Good afternoon. Myself Praful Ranjan and this is Digital Signal Processing Laboratory experiment number 3. This part is divided into two parts. First part is focusing on designing M-point moving average filter to smooth out the high frequency noises, and the another part is to design the first order, second order and central derivative filters to emphasize the high frequencies portions in the signals. So let's move to the first part, M-point moving average filter. So first one is we have to write the difference equation. So difference equations come from its mathematical definition, which is written like this: y of n is equal to the summation of x of n minus k going from 0 to m minus 1 divided by total number of average, that is m, and these are the indexes. Yn is current output, xn is current input, and these are the past output, and m is the length of input, and n is shows the sample number. So what is its significance? It's a there Its a basic function is to create a series of average values of different subsets of the full data set. It takes some parts from like a first to m previous values and sum it, and after that it divide to average it. So in that process it reduces the noises. Second one is to obtain the transfer function of this system. So from the definition, this is its a definition of transfer function, and mathematical expression will come like 1 plus z square plus z cube up to z to the power m minus 1 divided by z to the power m minus 1 and whole divided by m. So here is this is the definition. This is the derivation of h of z, and if we consider the GP series, then it will come like this, and where we can't say that z is equal to 1, and these are the denotation. And now comes to significance. Transfer function is used to relate the input output signal. It also gives some idea about the stability of the system. So it's help also finding in poles zeros of the system. If we encounter a poles, then we can say that the system become less stable, and if we find a zero, then it become more stable. And the frequency response is the also same. If we will put the e to the power z omega in h of z transfer function, then we will get the frequency responses. So frequency responses of the system is important to analyze the signals in frequency domain. So we convert the signal from time domain to frequency domain to analyze its signals like its higher component frequencies and periodicity, all these things. Next one is the so after calculating it is this one is its frequency response, and now we have to assess the magnitude response and phase response. So magnitude response is nothing but the absolute value like magnitude of the frequency response, and the phase response is the angle of that. So this is the mathematical representation. And next, this is the same code for the plotting. This is the expression for the code, the plots, and the plot is something like this. I have plotted for m is equal to 10, m10, 25 and 100. So m10 it is like it is also smoothing the noises, but in whenever we are increasing m, it is more smoothing the noises, means it is reducing the noises, we can see from here, and giving the importance to the peaky datas like this one, it is more smoother. No, and it is giving, as we are increasing the m, its magnitude response is coming more bigger, and the noises are reducing. So these are the different data for m is equal to 100. As we are increasing, we can see the high frequencies noises are reducing. Next one is to find the pole zero. So pole zeros we can also find from the h of z from transfer function. If we will find the roots of the numerator, then it will be give us zeros, and if denominator, it will give the poles. So from computing, we have get the like m minus m minus poles at z is equal to 0, and poles zeros at e to the power minus z 2k pi m 2k pi divided by m, where k goes from 0 to m minus 1. And this is the code for plotting, and these are the plots. So we can say for m is equal to 10, there are 9 zeros poles at z is equal to 0, and there are 9 poles, sorry, zeros, 9 poles which are distributed over a circle of radius unity. Similarly, for m is equal to 25, m is equal to 100 and 50. So let's come up or to be its significance. So addition of poles to the transfer function has the effect of pulling the root locus of the right, making the system less stable, and addition of zeros of the transfer function has the effect of pulling the root locus to the left, making the system more stable. So if we encounter a zeros, then it make more stable, and if we get a pole, it may make it less stable. Now here are the code to plotting the uh, magnitude responses on a single plot. So we can observe that it is m is equal to 10. For m is equal to 10, the lower frequencies are also magnifying, but as we are increasing m, it is reducing, and only the higher frequencies, low frequencies, m is equal to 10, higher frequencies also uh, magnifying, but as we are increasing m, it is decreasing, and the only peak is coming in the picture. So here, as m is increasing, the magnitude response becomes more smoother, and the noisy frequency components are becoming less and less, while keeping important peak as it is. So now this one is we have to plot the here we are taking some example of ECG and PPG. We will plot some examples of ECG and PPG for 2 seconds, and for taking m is equal to 10, 25 and 50, 100. So these are the codes, and these are the graphs which are coming. We can see this is the signal, and for m is equal to 10, it is smoothing the signal. If you will increasing the m, it is more smoothing the signal. Similarly for 50, it is more, but we can say as m is increasing, the peak values are also smoothing, which we don't want. We want to retain these peak values. So we will choose proper aim to design the aim point moving average. We will choose some proper, like aim is equal to 10 and 100. We will choose in between these. So this is the for PPG signal 20 dB. We can say here. We can see here these are the plots. Which for m is equal to 100, the peak is like dying. There is no peak. It is for 20 dB, and this is for PPG signal, and These all are PPG signal, and these are the ECG signal 50 dB, 5 dB. We can see this, like for as we are increasing M, the noise are reducing, but also the peaks are dying. So we will take some proper values of M to design the M point moving average filter. So from plots of signal we can see that as we are increasing the length of average, that is M, the signal is being a smoother and a smoother, which means we are reducing the noise significantly with M, but also we are seeing as M is increasing we are losing the important peaks. If we increase M more and more, the peaks will disappear, and which we not want. We want to retain peaks, so we need to choose proper M for signals to design M point moving, which we have already discussed. So we will move to the second part. So in this one we have to design the first order, second order and central derivative filter to emphasize the high frequencies portions of the signal. So these are the difference equations for first order, second order and the central derivative. Another one is obtain the transfer function. So similarly, by its definition we will move to derive its definition, its transfer function. So first order, this is the transfer function. For second order, this will come as its transfer function, and for central derivative it will come as like this. So as we have already discussed, transfer function is used to relate the input output signal, and it's also give some idea about the stability of the system. We will see in the result. And also for frequency responses, we need to put the e to the power j omega in hz instead of z. So we will get like this. These are the frequency responses. And next one is to sketch the magnitude responses and phase responses. So like we will take its magnitude, which will come like this, and angle like this for first order. Similarly for second order, for central order this will become. So these are the codes for plotting. So we can see this is coming like a high frequencies. For frequency at 0 it is giving 0, and as we are increasing it is giving the high values. After that it is repeating. So these are the magnitude responses for first order. This is for second order, where the in this one we can see that angle is coming pi, and this is for central derivative. We can see that its magnitude response is coming 2, maximum value is 2, and for it 4, and this one is 1. So it is like not magnifying the values, and these are magnifying the values. So magnitude response gives idea for which frequency output is amplifying, attenuating, and phase response tells about corresponding phase of output with respect to input signal. So we will see in coming pictures. So find the poles and zeros of the system. Similarly, uh, after finding roots of in of z, like a numerator and denominator, we can get the poles and zeros. So for first order derivative, poles are coming at one pole at z is equal to 0, and zeros at z is equal to 1. Similarly for second order derivative, poles are coming at 1, z is equal to 0, and zeros z is equal to 1. Two zeros are there. For central derivative also, poles is equal to 2 poles, and which is coming at z is equal to 0, and 1 zeros at z is equal to 1, and 1 zeros at z is equal to -1. we have already see the values of the poles and the zeros of system determine whether the system is stable and how well the system performs. So that's why we are studying the poles and zeros. So these are the codes for plotting. We can see this is coming the zeros at z is equal to 1 and poles at z is equal to 0, 1 pole. Similarly for second, there are two zeros at z is equal to 1 and 1 pole. Similarly for this one. So now we have to obtain the output of the derivative filter for the PPG and ECG signal. Okay, so this one, these are the same which we have written above, and these are the notations. This is the code where just I am taking first I have loaded the signals, and then I am extracting the data from the signals, and after that I have taken 2 second from 2 second to 4 second for every signals, and one by one I am calling the function to plot. And in plot we are defined I have defined the y value as its difference equations which will give, and I am subplotting these values. So the result will comes like this. This is the original signal, and this is first order derivative output, and this is second, and this is for central. So we can see in this one it is also amplifying the noises for first order, and the second order it is like smoothing it more, and for third it is reducing the noises also. So this is for ECG 20 dB and this is for ECG 15 dB. Similarly I have plotted for PPG. In PPG we can see that this is working as high frequency high pass filter. In this one we can see that it is also amplify high, it is high pass filter. First order derivative is working as like a high pass filter, which is also amplifying the values of noises. So we will move to second order derivative, which reduces, which also smoothes some noises, but it also amplifies some noises. So the third one is output of central derivative, which is smoothing the noises. This is for PPG. So from the magnitude response and the above outputs, we can see that the first order derivative is working as high pass filter, which magnify the high frequencies and sometimes also amplifying the noises. The second order derivative filter play a role to filter these noises too. Central derivative also reduces the noises and it's better filtering than second order. Central derivative filters reduces the noises to a significant extent, which we can observe from these graphs. We can see here these are the noises. Thank you.